right, how's everybody doing today? The revolution is here. All right, we're going to talk a little bit about Solr, a little bit about Lucene and Hadoop, and the way we do those things at Etsy. So my name's David Giffin, and I've been working at Etsy for about 4 years now, dedicated to search. And today what we're going to talk about a little bit is the history of search at Etsy, sort of some of the pains and process that we've gone through and some of the wins that we've encountered. And then we're going to talk about I'm going to give you a sneak preview of some of the stuff that we're doing right now that's not in production yet, which is our new indexers. And then we're going to talk a little bit about replication, which you might have heard of some of these things before in other blog posts and such. So let's continue on. So about Etsy, Etsy's the marketplace for handmade and vintage goods. It's got a variety of everything on Etsy. You can find art, clothing, jewelry, you name it, you'll probably find it. You need some feather hair extensions. And what Etsy does is it really creates a more human economy. So we're not just dealing with goods, but we're dealing with the people that actually craft the goods, right? So this is really kind of dear to my heart because my wife's actually an Etsy seller. And so, you know, we're doing sales at the house, shipping stuff out. And so not only do I work on the website, but then, you know, we actually have our little shop that's on there too. So she sells beautiful paper cut creations to people all over the world, lots in the UK and Australia, and so it really is a truly global marketplace. So Etsy itself does, you know, we've got about 13 million listings today, 39 million unique visitors. Alexa ranks us about in the top 50 in the US and the top 200 in the world. So a lot of people depend on Etsy, and we have a team of 100 engineers that are all working to make Etsy a better place. So let's kind of move on to the architecture. Basically, we do a standard LAMP stack. So everything's Linux, Apache, MySQL, PHP, all the standard stuff that you'd have on any other web server, or website, that is. So the only thing that's interesting about this is that search, we actually have our own custom search server that we create that actually has Solr embedded in it, and then Thrift that actually sits on top of that. So when our webs talk to our search servers, they actually talk Thrift versus talking you know, HTTP and sending raw queries. And the reason we do this is to really create a contract between the search servers and our front ends. And so, and the other secondary reason is that you know, it's actually there's more data and more to push across the wire if you're doing JSON or XML. So Thrift actually, you know, is a tighter protocol and ends up saving a little bit of traffic there. So in this example, hats for cats, we'd run that query, and then what we return is just the listing IDs for that particular query. And then we have to go through a hydration process, and that's a standard thing where basically ask Memcache if it's got the listing. If it doesn't, go ask the database, da-da-da. And then what you get is a whole lot of cats with a whole lot of hats. So I like the Mario one myself. It's pretty sweet. So a little bit about the history of Etsy and search. I started back in 2007. Back then, we had about 1 million listings. We had a single master database that was our main database. It had everything in it, you know, all the transactions, all the listings, everything. And at that point in time, we didn't have Solr. We actually had T-Search. And if you guys don't know what T-Search is, it's basically search that's implemented within Postgres. And so what they found back before I started was that T-Search, you couldn't just hit the master database anymore because it was killing master. So they ended up implementing what they called a baby database, which was basically a Solr slave, if you think of it that way, that was just the listings table. So they replicated out the listings table, and then they created their gen and gist indexes on T-Search, and hit those instead of hitting the master server. And in order to pull the data across, they actually had this thing called the baby replicator, which would actually query the master database and then find out what changed, similar to data import handler, and then update those babies out there. So in 2008, I was like, search is starting to get really slow. Beads was taking about 60 seconds. If you search for jewelry, that was, jewelry is probably 2/3 of our site. So when you did that search, it would take forever. So I said, we need to change out what we're doing on search, and we need to use Solr. So that took a while to get Solr in house. But once we did it, it was amazing. I mean, we went from 18 servers, all pegged out, to we could run it on 4 boxes, so it was awesome. There was only a few little things that we had to do in terms of getting the updates into Solr, because we already had this baby replicator process. And so what we did is just hack that, had it send XML down to Solr, and then we implemented the data import handler for if we had to do a full reindex. So 2009, not a lot changed except for the guy that did the baby replicator, he went somewhere, and baby replicator started to slow down. It was having issues. I was the only one that knew about it. So we want to get something a little more standard. So we went ahead and implemented ActiveMQ. And we also added a couple more slaves. So with ActiveMQ, what we did is basically whenever something changed on the website in PHP land, we'd actually take that XML, shove it into ActiveMQ, and then feed that down to Solr. So eventually it'd get there. Then in 2010, everything changed because we were hiring tons of people. We needed a infrastructure that was going to scale to not only the website, but then the developers that were all coming in-house. So we needed to rebuild the search stack so that people can create a new core easily and do all this. So the whole idea of the embedded Solr within our own service came to life. And what we did is end up taking all of the PHP code that did all of our crazy queries. We implemented that down in the search service. And so when you hit Thrift, you actually then run all of those chunks. And the nice thing about it was, before you had all these PHP unit tests, and then you'd have potentially search unit tests. So this actually made it so that we could just run a single JUnit process and make sure everything was working the way it needed to. Added a couple more slaves, and then we started creating a custom import handler, because the queuing process that we were doing, whenever we do a full index, was just taking hours and hours and hours. So we actually created something similar to the data import handler, but with some caveats, and we'll talk about that later. So 2011, now we've got 10 million listings. We're starting to actually shard our database, so now we don't have this monolithic master. And at that point in time, this custom import handler was really cool, because now we could actually go out and in parallel hit all of our shards and actually return that data back and then shove it down, versus having to go serial to each one, those kind of things, which I'm not sure you can do with data import handler or not. But and then the future is now, we're not sure how many listings this Christmas, but usually things double. And right now we're looking at how we're going to change our indexer again to deal with some of the issues that we're having now. So what did we learn? Oops. We learned that Lucene and Solr, awesome. T-Search, not so awesome. We actually had our Omni IT folks. These are like Postgres experts. They went in, deep dive, try to figure out why T-Search is taking long. There's an article about it. You can read it. Just not that exciting. Let's see. Trunk is awesome. It's saved our butts many times. For instance, when we were doing the data import handler originally, back then the fetch size didn't exist for the Postgres driver, so you couldn't actually query all 13 or however many million listings there were at the time, because it would actually suck up all the RAM on your JVM and your host. So we basically just pulled down trunk. It had the fetch size in it. We were actually able to then keep the memory small. Everything's happy. Good stuff. And then Deployinator. I mean, Deployinator completely changed everything for us. And if you guys haven't used it, you need to check it out. But let me give you a synopsis of what it does. Really, it's the way that everybody deploys code at Etsy. So for search, what we do is we have a QA, a princess, which is like staging, and prod. And in staging, what you're doing is you're actually hitting live databases and live, traffic in that scenario. So the first push, what you do is you actually push to QA. It goes to a Solr master, 2 Solr slaves, and then kicks off a Jenkins build that actually will run all our unit tests and that kind of thing. And then if that all goes well, then you push on to princess, and then you push on to prod. And there's some magical rainbows and unicorns that we have in the search area. It's pretty sweet. So check out Deployinator. And so with Deployinator, the other cool thing is that we created these smokers. So with our embedded Solr service, what we can do is we actually can hit the Thrift API internally and then actually make sure that searches run on a given index. And so for every core that we have a smoker that goes along with it. So when you push to QA, you actually run that smoker, and Thrift won't even accept any connections until the smoker passes. So this way, everything's off until the thing actually works. And if for some reason something goes wrong, we actually roll back to the previous version. So smoker's a cool concept that you might try implementing. StatsD, if you aren't using it, you need to be. StatsD basically it's a cool little tool that anything on your network, you can send a simple little UDP packet that will say, count this. And so we count everything. We count page performance. We count, I don't know, when replication happens, how long it took, da-da-da-da-da. Everything goes through StatsD. And so some of the things that we're looking at in terms of performance is the 95th percentile. For us, we have sort of a service level agreement that we set for ourselves that every search needs to be under a second. And so in order to do that, we use StatsD. And what you see here is this is actually a stack of all of the different pieces of code on the site that actually get hit when you do a search. So there's like starting, building the query, actually performing the search, rendering the templates, creating the event logger, search ads, all that stuff. It's all there. And you see the blue stuff is actual searches. And so you can see the variance that's going on right now. And so it's an ongoing problem that we're trying to solve, is to get that smoother and obviously shorter. So one thing that we did to make it shorter just recently is implemented this idea of a top-level cache. And so Solr has caching, it has filter caching, it has all these things. But what we found is that we needed even more cache. And we looked at, okay, let's look at memcache, different ways of doing it. We tried, I don't know how many different ways, but what we ended up coming up with, what the end result was, when you do a query for red dress, what we do on the search server side is we'll actually query that query for red dress. We'll get 10 pages of red dresses, and then we'll cache the actual Thrift response that's going to come back to the PHP side, and then we'll, based on which page you're on currently, if you're on page 2, then we send back the page 2 results, so on and so forth. And we actually found that was faster than doing the same implementation on the PHP side and actually hitting memcache and then caching that same Thrift response. So Solr's fast, JVM's pretty fast, just something to think about. Etsy properties. This was something that we implemented when we redid all of the indexers with our custom indexer. So with data import handler, you have this idea of the last modified date. And this actually just has a timestamp, if you guys can't see. It just says like some date. And So with Etsy properties, what ends up happening is every index that we have is actually stamped with Etsy index properties. And so this way, if for some reason we build an index that's bad or has something wrong with it, we can roll back to the old index. That index knows exactly when it was updated last, and then we can just replay whatever we need to replay against it. So that's awesome. Whenever we do a new index, we always check the index size. If it's 50% less than the current index size, just don't even install it. When we're doing incrementals, if for some reason the incremental is too old, like we're gonna query 10, 100 days worth of data, we're gonna kill our databases. It's ridiculous. So don't do that. Also, we store nothing in terms of Solr. And the reason being is that we really want to keep the index as small as possible, so that way we don't have to shard in the foreseeable future. And we just want it to be as fast as possible. So by storing nothing, index size is reduced and we're able to hit things faster. The memcache, the other side of things, they get the same data just as fast as Solr would, or faster at times. Also, keeping denormalized data. So as we shard and as our data gets all over the place, now it becomes a time when it's like fetching the data and making a listing object it's all over the place. So what we do is we have a PHP denormalizer process. It's the same stuff we use on the web stack when we're going to go ahead and render a listing. We take that, we create a JSON object of it, and then we shove it down into the search database. And the reason it's a JSON object is a couple things. One, it's schemaless, so we don't have to worry about changing a schema all the time and dealing with that. And when we're reindexing, we need all the data anyways, right? So there's no reason to go get all these columns or fields or whatever. Just store it in JSON, keep it simple. When you do a full index, you always want to update and apply the incremental, so that way you actually bring it up to date. It's a good idea. And then when that breaks, because your actual indexer takes 12 hours, and then the incremental takes half an hour, then you have to apply another incremental. So, and then still indexers crush your databases, so you have to retool the whole thing. So that's what we're doing today, is looking at how to basically run MapReduce jobs to actually generate indexes. So first of all, why HBase? Well, one, HBase scales easily. All you do, add more machines. It allows us to create MapReduce jobs that just run across it. There's no, we don't have to go hit other servers, that kind of thing. It's all, it makes sense for MapReduce. So in doing that, then all we do is we take our JSON object, we shove it into HBase. And HBase has a Thrift interface, so you can just talk to it and write down to it. So listings denormalized, it looks like that. It's basically listings denormalized, and there's listing data, which is the JSON object. That's about it, nothing to look at here. And then the interesting part was that we actually had to keep track of when things change, because HBase is just a key value store, right? So all you can do is look up by some ID. So what you don't know is what changed through the course of what you're putting into the HBase database. And so what we do is we actually keep track of which listing IDs changed. And so in this particular instance, what you see is PKS, which is primary keys. And so that's just a list of listing IDs that changed on a given date. And then what we can do is query by date into this and get those listing IDs that we need to update in our indexers. So now we got our data in HBase, and now we need to actually create an index. And in order to do that, there's a couple different patches that are out there. They're pretty stale. This one kind of fit the bill for us. It's about 3 years old. It's a good starting point. It shows you how to build basically indexes out of CSV documents. And it provides basically the Solr output format. And what that looks like is this. what ends up happening is you fire off a MapReduce job. In your reducer task, it actually fires up an embedded Solr server, and within that, it actually will write to only a POSIX-compliant disk, because that's all Solr can write to at the moment. And then once that index is generated for that reducer, it will then copy that chunk of index back up into HDFS. So for a MapReduce job, if you guys aren't familiar, there's the mapper, and he'll actually take all of your objects and then map them into some intermediate data, so then your reducer can do something with that. And so the reducer part is where this comes in, and what you'll do is you'll say, I want to run 40 reducers for this particular index, and it'll generate basically 40 sharded indexes out there for you. So one of the couple things with 1301, it wasn't great with the multi-core configs. That just didn't work, so we had to do some hacking on it for that. We had Solr config issues because we have a whole lot of environment variable specific stuff that goes on in the configs. So I added env support. So basically in your Hadoop job, you can just say env.something, and then that gets passed into the actual Hadoop job, and then set as a system variable for Solr. And also implemented the old and the new style because the patch moved over to the new style, but Hadoop says that the new style isn't supported yet, or at least Cloudera. So we did that. And then the next part is we started digging into, well, we've got like, I don't know how many indexers, 13, 14, maybe more. And in order to do that, the mapper portion, what we were ended up doing is taking whatever data that we had from HBase, let's say, creating a listing object, which then got written to intermediate data, and then we'd have to take that intermediate data and then create a Solr document out of it. Well, that was kind of a pain in the butt. So what we did is actually just extended the Solr input document and created a Solr input document writable. And what that allows us to do then is use all of the standard indexing code that we already have today and just create a Solr document and then write that down as intermediate data. So this is a big win. It'll allow us to migrate all of our indexers really quickly, and we'll probably be open sourcing this hopefully soon. And then the other thing we did is we implemented Oozie, and I don't know if you guys know, but Oozie is basically a workflow engine for Hadoop. What Oozie allows you to do is basically kick off a workflow, and that workflow can do whatever it needs to do. With our Oozie job, what it does is I think I have it here, but the problem with Oozie is it doesn't support HBase. So what we had to do is we had to create this scan string generator, and there's a URL to see that. Basically, what ends up happening is you can't actually pass the mapper table name into the job configuration or the workflow configuration for Oozie. So we had to actually implement this class that then allows you to create scanners for HBase. And then the overall architecture looks like this. So if you guys weren't getting the picture yet, now here's the picture. So indexer kicks off. It starts an Oozie job. That runs a map reducer. The mapper is going to suck out the data out of HBase. It's going to run the reducer. The reducer was really just the Solr output format. That's going to write to disk locally and then to HDFS. And then what we have to do is copy all of those indexes down to our master and merge them all together and then bring the index live. So indexer main.action is an action that we created that's specific to the 1301 patch. And it'll actually implement all of the things you need to do to kick off the Solr output format and all those things. So we'll have that out there soon. And then we integrated deployinator into this whole process too. So with MapReduce, you always have to have your actual jars up in your Hadoop cluster. And so what we did is when you actually kick off a build, and also you need your Solr config out in your cluster too. So when you kick off a build, what we do is we actually we zip up the Solr config, push it out to HDFS, and all of the dependent jars and the Etsy jar and all that stuff all goes there. And then we're able to run our actual indexers. Let's see, and then once we actually got this running, we needed to actually compare the index that we had, the new index that we've created, to the old indexes that were generated out of the database, just to make sure everything was right. And there wasn't really a good tool for this, and so I created one for that. And so this index compare tool basically does this. It's like a low-level Lucene comparison. So you can give it index A, index B. You have to give it your primary key, and then you tell it a percentage of the index that you actually want to compare, and it'll actually go through and find document ID out of this guy, query that same document out of the other guy, because they're going to be different IDs because two different indexes, and then verify those two things are the same. And when you see the hashing thing, the other thing that we did is in that Solr document writable that I was talking about earlier, we implemented a hashing scheme so that you can actually take the Solr input document format. It actually will iterate through all of the fields that it has and actually create an MD5 SOM in a hash field. And so that way you can actually just compare the raw Lucene indexes on disk versus having to create these, what we used to do, which is some crazy queries here, queries there. Do they look the same? We don't know. Yeah, so this simplifies all that. And then there's the whole copy and merge thing. And this is another class that we're looking at where what we're going to do is be able to pull down all those indexes in parallel, and then you'll be able to specify merge factors and all those kind of things so that you get the right index that you want on disk before you go live. And so this will all be open sourced hopefully pretty soon, going through that process now. So we're going to switch gears and talk a little bit about replication. Some of this is maybe stuff you've seen before. But basically, here's the problem. Every night we used to do, or we still do, optimizes. And so when that happens, then we basically generate a whole new index. So about 13 minutes of that is the optimize, and then there's an hour of it that's actually pulling down the index. And so what we found is that really our master was just getting pegged by pulling down this index. And everybody's just going slow to get it. And it looks kind of like this if you look at the network graph. Just dismal performance. You know, we're like 8 megs. You know, netcat was working great. I mean, you can netcat all these nodes. Everybody's happy. But for whatever reason, just Solr replication was just crawling. So we said, well, let's fix that. And so we've implemented bittorrent replication. And what we did is our ops department kind of went out and they said, you know, let's try different ways of getting this out there. So we tried, you know, multicast. That brought down the network. Fail. You know, we tried all sorts of different things. And we finally came up with, you know, this tornado piece that was able to actually shove the indexes out, you know, within, I don't know, a minute, I think it was the end result versus an hour. And then we said, okay, well, that's cool, but, you know, it really doesn't integrate well with Solr. And, you know, we really like to contribute back to the community. So we looked at how we could actually integrate BitTorrent together with Solr. And what we ended up doing is finding a tool out there called Torrent, which the folks at Torrent created, and basically took what we had in the HTTP replication handler, ripped out the HTTP bits and shoved in the BitTorrent bits. And it's a little bit different than that, though, because when you actually kick off a commit, you actually have to create a torrent file on disk. And then once that torrent file is created, then the masters will suck it down, and then they'll have that torrent file. And then they're able to then hash whatever files they have on disk and compare them to the torrent. And then what you do is you just pull down the delta of those versus having to get all of the index. And the nice thing about that too is that when I don't know if you've ever done this, but if you do a whole lot of commits to your Solr server, HTTP replication will like have to retry over and over again to pull down data a lot of times. And so with BitTorrent replication, it always has this torrent file, and it's always downloading the files to part files versus the actual index. And so those part files just keep getting updated throughout each commit as time goes on. And then the BitTorrent stuff happens. They all hit this announce URL. The announce URL tells about what's out there, and everybody sucks down and shares the data. So at the end of the day, we were able to actually saturate a box's NIC, right? We're pushing 34 meg or whatever. And then if you look at the overall, this is, I don't know how many, I think might have been 16 at this time. So we're pushing a 350 meg out on our network. So this is huge. I mean, it's way faster, and actually we're slowly migrating all of our other larger indexes over to BitTorrent. So this has been in prod since last Christmas, and this will be open sourcing soon. I need to submit a patch and do all those fun things with the Solr folks. And we're always hiring, so if you need a job, bam, come on. Thanks. The question was, can I tell you the queries per second and the specs on the Solr slaves? Our Solr slaves, they're basically all the same box. I think they're running 16 or 32 cores. That's CPU cores, that is. And we run just like 100 gig SSD and 64 gig of memory on each one. So that's a Solr slave. Queries per second, I think we do roughly 500 queries per second at this point in time. Don't quote me on it. Yeah, so the question is, we update from trunk. How often do we do it, and what problems do we have when we update from trunk? So we try to update every, before Christmas to get all the newest performance stuff for sure. And then we do it as sort of on an as-needed basis. So we kind of look at what's going on out there and try to pull in a version that we think makes sense. In terms of dealing with the issues from trunk, what we end up doing is we end up having a cluster and a B cluster, and Deployinator can deploy to either the A or the B cluster. So we'll actually deploy a build of our everything with trunk and deploy that to our B cluster, and then we'll turn on traffic to the B cluster and see if it falls over. Oh yeah, so the question is, when we say store nothing, what does that mean? Because you have to get the data from somewhere. So when I say store nothing, I mean store nothing in Solr. And so Solr, you can actually say, for each field, you can say store this field, right? And it'll actually take whatever input you gave Solr and put that in the index for you. So that way, when you query, you can actually get that data back. And if you're using some of the newer stuff, which we were talking about, the stump for chump, you kind of need to turn that on in order to do the updates, But we'd rather not do that. We actually would rather not store it there. And so where is the data? Well, let me tell you what we do store. What we do store is just the listing ID. And then where we get the data from is, it's all in our database. And so that's the same stuff that the PHP denorm stuff that I was talking about earlier. Same exact code actually goes out, hits some Memcache, hits the database, does all those things. Why do we optimize every night? Good question. Because our merge factor is way too high, is the simple answer. The long answer is we're not going to eventually. So with trunk, there's all the new stuff with the soft merging and all that. So eventually we're not going to. And actually, as of Monday, we were supposed to not do it, but I've been here, so I don't know if that happened. Do we do anything with recommendations? The question is, yeah. So with recommendations, our system is, it's all offline. So we end up actually running like MapReduce jobs on big data stuff. And then we'll create let's say related searches. We'll create an index for that and then query that. So it's not in Solr per se. It's just, it's actually more of a MapReduce job for us. Thanks again.